Wait, what? This one.
Oh.
Oh, mark on that. Yeah.
Wow.
Yeah. Oh, no way.
No way.
All right, good morning. Yeah, good morning, everybody. Welcome. It's our last class. Almost done. Same reminders as earlier in the week, so don't forget about the second little part of Chapter 9 that's in a recording. Your last achieve is due Monday at the end of the day. You also have quite a few learning curves if you'd like to complete for review. So questions are good for review, and then also when you complete them, that will count towards extra points towards your final exam or unit exam too. Those are also due at the end of the day Monday. Keep in mind there are some questions on the learning curves that can't remove individual questions, so some of them might ask about content that we didn't cover in class. If you are unsure about those, feel free to take a screenshot, send me an email. I'll reply as soon as I can. Next Monday, we don't have official class, but I'll be on Blackboard Collaborate during class time for this section and my 9 a.m. So feel free to come to either one or both of them. It's just like an office hour. So I won't have my 1 p.m. office hour, but I'll be available at 9 and at 11. And then our final exam is next Wednesday at 11 in this room. Don't forget your pencil, eraser, calculator, and if you want like a water or something. Just so you all know, with the ACS exam, faculty have to be really careful about distributing them. And so one of the restrictions we have is that students will have to put all of their stuff except for your pencil, eraser, calculator, water at the front of the room. So when you come in, you'll put all of your things at the front. Just take what you need to your seat. Again, of course, we'll sit every other seat. And then we have an hour and 50 minutes, but if you finish early, you can leave early for this one. So, yeah, I'll remind you of all of that on Wednesday. There's 70 questions. Yeah. They're all multiple choice. And don't forget it is cumulative. So don't forget to review some earlier chapters as well. Okay, so at the end of class Wednesday, we started talking about electronegativity. So electronegativity is a measurement of how strongly an atom holds electrons that are shared in a bond. So if we have an atom or a molecule, like let's think about water. H2O, we have two bonds from an oxygen atom to hydrogen atoms. The electrons in the bond are shared between hydrogen and oxygen, but the electrons in the bond are not shared equally. The atom with a higher electronegativity has a stronger pull on those electrons due to its higher effective nuclear charge, so more protons in the nucleus, which causes those electrons to be closer to the atom. So if we look at this periodic table has electronegativity values. There's a way to calculate these, but we won't be doing that. 4 different elements. So oxygen has an electronegativity value of 3.5. Hydrogen electronegativity value is 2.1. So hydrogen has a lower electronegativity value. The electrons that are shared in the bond between oxygen and hydrogen are a little closer to the oxygen atom. This is the same trend as effective nuclear charge. So elements with higher effective nuclear charge, which is top right of the periodic table, have a higher electronegativity. It is the same trend as ionization energy. Elements with higher ionization energy, top right corner of the table, have higher electronegativity. Yeah, already said effective nuclear charge, right? Okay. The last trend we talked about was ionic size or atomic size. This is the opposite trend. So our larger atoms are down here. Electrons are further away from the nucleus. Smaller atoms are up in the top right corner. Electrons are closer to the nucleus. Those atoms have a stronger or higher electronegativity. So in a molecule like hydrogen fluoride, fluorine has a higher effective nuclear charge than hydrogen. So electrons are more attracted to the fluorine. So HF, we have a covalent bond, sharing of a pair of electrons between fluorine and hydrogen, but the electrons in that bond are closer to fluorine. So this means that in the molecule, fluorine has a higher electron density around it. Electrons are closer to the fluorine. So we represent that with a partial negative charge on the more electronegative atom. So in this case, that's fluorine. Fluorine has more electron density than hydrogen. So we say it doesn't have a formal negative charge. We calculate that with the formal charge formula. But it has a partial negative because it does have some extra or some additional electrons around it. This symbol here is lowercase delta. So delta with a minus sign means partial negative. Delta with a positive sign means partial positive. So we can assign atoms partial positive or negative charge if we have a polar bond. So polar bond because the electron distribution is not equal. We have more electron density around fluorine. We can also show a bond is polar with this arrow. So the arrow points towards the partial negative atom, so the more electronegative atom. And you can think of, we have this hash line on the other side. If you just look to the left of my hand here, that looks like a positive symbol. So we write this hash symbol next to the by the partial positive atom, and we point the arrow towards the more electronegative atom, the partial negative atom. So our arrow points to more electronegative atom. If we look at something, or not something, but if we look at water, like we did on the previous slide, oxygen is more electronegative than hydrogen. So the bond between oxygen and hydrogen is polar, and it has a polarity towards oxygen, where oxygen is partial negative, hydrogen is partial positive. And we can draw that same arrow for both bonds. Both hydrogens are partial positive, the oxygen's partial negative. That polarity arrow, sometimes this is called a dipole. I don't know if you're going to see this on active, but dipole or polarity are referring to the same properties. So we can draw that dipole arrow per bond, or we can say overall this molecule is polar and just draw one arrow to show the molecular polarity, which is still, again, towards our more electronegative atom. So we can use electronegativity values to determine if we have a polar bond, if we have a nonpolar bond, or even if we have an ionic bond. So F2, this is a covalent molecule, fluorine bonded to another fluorine. 2 electrons are shared in that single bond. That single bond is between 2 fluorine atoms. Fluorine and fluorine have the same electronegativity, so one atom is not holding on to electrons stronger than the other because they both have the same effective nuclear charge. So these electrons are shared equally. This is a nonpolar covalent bond. So we would not assign partial positive or negative. We would not have a dipole arrow.
Yeah. This is a little off topic, but how come you don't just like put 3 bonds when you're connecting 2 fluorine?
Yes, because fluorine already has 7 electrons. So if we just draw, it's in the 7th column, so it has 7 pairs of electrons. So if you have 2 fluorine atoms, each fluorine just needs 1 more, so it just has a single bond. Okay, and then hydrogen fluoride, which we looked at on the previous slide. Fluorine is more electronegative than hydrogen. We look at the electronegativity difference here, 4.0 minus 2.1, we have an electronegativity difference of 1.9. So electronegativity difference greater than 0, greater than around 0.5. The cutoffs won't be super important for our class. But this is considered a polar covalent bond. So there's a difference in electronegativity between hydrogen and fluorine. Now, if you have a large difference in electronegativity, the electrons in the bond are no longer shared. They're owned by the more electronegative atom. So if we have electrons that are not shared, and the bond is occurring between an atom with extra electrons and an atom with fewer electrons, this is an ionic bond. So a large electronegativity difference, for example, between cesium and fluorine, the electronegativity difference is 3.3. This would be an ionic bond. So let's look at this example here. I think you all have these images. So in this learning check, we have 3 groups of bonds, so part A and part B. And your task is to arrange these bonds from least polar to most polar. So least polar would be smallest difference in electronegativity values for the 2 atoms. More polar would be larger difference in electronegativity values for the 2 atoms. Don't look at electronegativity values, just use the periodic table. So try to consider which atoms have higher or lower electronegativities. I'll give you all a minute or so to work on this before we go through it.
Yeah, because there was.
Is there like a
Absolutely not. So today's a business thing. That's the question. So
Isn't it like a primary? But like, there's also the up and down. You just have to go electronegativity.
Yeah.
Is it most?
Just think of it like, I know this A is like a metal. I think it's 1, 2, 3. Because they all share carbon, right? Sulfur's here. So your electronegativity increases as you go up and to the right. So sulfur's the lowest on that one. Then oxygen is the lowest. They all share carbon atoms. So you just bring sulfur oxygen based on the electronegativity. So for your furthest up east.
that's the one thing to be sure. Yes. But really, and then here's like translation.
Just very no. All right, first one, we are looking at different atoms bonded to chlorine. So of these 3 atoms in the previous column, which would result in the least No, the most polar bond. Which would result in the most polar bond? TE to CL. How do you know it was TE? It's the farthest away, sure. So chlorine is a pretty electronegative atom. It's in the 7th column all the way to the right. All of these have lower electronegativities than chlorine. The lowest electronegativity in this column is TE. And then how about the least polar? Yeah.
It's gonna be S to CL.
S, yeah, they're right next to each other, so they'll have pretty similar electronegativity. So this is least polar. And most polar. How about carbon bonded to oxygen, fluorine, or sulfur? What's the most polar bond? Carbon to fluorine. Yeah. Carbon to fluorine is our most polar bond. Fluorine's the most electronegative. All of these atoms are probably more electronegative than carbon because they're further to the right. Now we need to compare oxygen and sulfur. Well, what do you all think? I'll take any explanation here. We're looking for which element, oxygen or sulfur, is more electronegative, and that will tell us it has a more polar bond to carbon. Yes, oxygen is more electronegative than sulfur. It's further up on the periodic table, higher effective nuclear charge. So oxygen has a higher electronegativity than sulfur. Oxygen and carbon will have a more polar bond because carbon is less electronegative than both. And if we go to electronegativity values, oxygen has electronegativity 3.5, sulfur 2.5, carbon is 2.6. So carbon and sulfur have very similar electronegativities. That's probably a nonpolar bond. We would consider that nonpolar because it's such a small difference. But carbon and oxygen, that's a polar bond. Okay, questions on electronegativity or polarity? Okay, we will continue to bond enthalpy. So we'll discuss how bond length and strength are related in the energies of different bonds. So bond energy is the energy required to break a bond. So any bond that is broken, energy is required to break it. So bond energies are positive because of that. Energy is required to break bonds. We look at ethanol, for example. We have 4 different types of bonds here, and each bond, depending on which atom is bonded to what other atom, and if you have any double bonds, that's different than single bonds to the same atoms. But each of these have different bond energies. These are not to be memorized. These would be provided if you need them. But this describes the amount of energy required to break a bond. So to break an OH bond, 460 kilojoules are required per mole of OH bonds. Now these are all known values, which are approximated, so we have average bond energies, in units of kilojoules per mole. So here is the table we will use for our PowerPoints. On Achieve, the table in Achieve is a little bit more specific, a little bit more precise. You might notice all of these end in a 5 or a 0, so they're pretty averaged bond energies. In Achieve, in the book, they have a more specific table, so if you need those values for Achieve homeworks, use the table that's in the book. When you're working on the assessment, values will be provided for you, and you use those values. So whatever you're working on, use the values that are provided. The values in the book are very similar, just a little bit slightly different, and so that might give you a different answer, and Achieve will mark it wrong. But a couple things to notice here. If you look, let's see. Carbon to carbon in this middle part, but at the top of this column, I'll circle it. Carbon to carbon single bond has a bond energy of 345 kilojoules per mole. Carbon to carbon double bond, the bottom, has a bond energy of 615. So as you increase in the number of electrons shared between two atoms, single bond, 2 electrons shared, double bond, 4 electrons shared, the bond is stronger. Stronger bonds are also shorter bonds. The atoms are closer together. They have more of an overlap of their orbitals. If you look at carbon to carbon triple bond, bond energy is 835 kilojoules per mole, so even higher than carbon to carbon double bond. The same is observed for other atoms. Here's an oxygen-oxygen. Single bond, 145. It's pretty low. Oxygen-oxygen double bond, 495. So much higher there. So same is true for different atoms involved in bonds. So this is all summarized on the slide here. So most of the bonds listed in table are single bonds, which involve the sharing of 2 electrons. Single bond, 2 electrons. Double bonds involve the sharing of 4 electrons. These are substantially stronger and shorter than single bonds. Triple bonds, which involve the sharing of 6 electrons, are even stronger and even shorter. So here we have some values. Carbon to carbon single bond, 345 kilojoules. Double bond, 615. Triple bond, 835. Carbon to carbon single bond length, 154 picometers. Double bond, 133 picometers. So stronger bond is a shorter bond and has a higher bond energy. Same thing with the triple bond, shorter bond and a higher bond energy. Now we can use these known values of bond energies for molecules to determine the change in energy of a reaction. So bond energies can be used to estimate the energy change for a chemical reaction. For example, in this reaction, we have hydrogen gas, oxygen gas, we're forming water. We're breaking hydrogen-hydrogen bonds, breaking oxygen-oxygen bonds. That occurs some amount of energy, or that requires some amount of energy. And then we're forming bonds to create water, which releases energy. Forming bonds release energy, breaking bonds absorb energy. We're going to skip the work. We'll do the work for the next question. The answer here is negative 475 kilojoules using values in the table in this PowerPoint. If you use the table in the book, the answer is negative 470. So again, it's close, just a little bit different. So this means we have a negative value here. This reaction is exothermic. This means that the energy released when water is formed is lower or is higher than the energy required to break the bonds in the starting materials. So let's actually do this calculation on this slide here. We have our provided reaction up here. Tell the person next to you what type of reaction is that. Do y'all remember what type of reaction this is?
Yeah.
What is it? What is it? No.
Ariana.
Are you saying virus?
Oh, yeah.
It's a combustion reaction. We have a hydrocarbon reacting with oxygen to form carbon dioxide and water. That's a combustion reaction. So there's some review from an earlier chapter for you. Okay, so if we're calculating the change in energy of this reaction, we use the formula at the top here. We add together the energy required to break the bond, so the bond energy of all of the reactants, and we subtract the bond energy of the products, because as those bonds are formed, energy is released. So we're subtracting the energy required, the bond energy of these bonds. Now, we have C3H8. If you're doing this problem, you have to first draw the Lewis structure to see what bonds are present in that molecule. C3H8 has 3 carbons, 8 hydrogens. We have 2 carbon-to-carbon bonds and 8 carbon-to-hydrogen bonds. So we need to add together 2 times carbon-to-carbon bond energy, 8 times carbon-to-hydrogen bond energy. We have 5 O2, so we add 5 times the bond energy of oxygen, double bonded to oxygen. Different energy than a single bond, different energy than a triple bond. And then we subtract the energy, the bond energies of the products. So carbon dioxide, each carbon dioxide has 2 carbon to oxygen double bonds. So we have 6 carbon to oxygen double bonds. Then we have 4 waters. Each water has 2 oxygen to hydrogen bonds, so we have a total of 8. So to actually do this calculation, we have change in energy of the reaction equals the sum of starting material bond energies for individual bonds. So we'll start with carbon to carbon. 2 times, I'm going to leave out units just for space, 2 times 345 kilojoules per mole. Then we have 8 carbon to hydrogen bonds, so 415, and 5 oxygen to oxygen double bonds, so 495. That's all of our starting materials or our reactants. Then we subtract the sum, the bond energies of all the bonds in the products. So 6 carbon to oxygen double bonds and 8 oxygen to hydrogen single bonds. The change in energy of this reaction is negative 1,695 kilojoules. Now remember, combustion reactions are exothermic. They release energy, which aligns with our calculation here. We have a negative change in energy of the reaction. So a couple things to be careful about when you're doing these questions is to make sure that you draw the Lewis structure so you know how many of each type of bond are present in every molecule. You use the coefficient and the number of bonds in each molecule to find the total. So we have 4 waters produced. Each water has 2 oxygen to hydrogen bonds, so we need to multiply the bond energy of oxygen to hydrogen by 8. Questions on this? Okay, well, we will go to our very last unit, last section here. So this is the first part of chapter 11. So we'll talk about VSEPR, valence shell electron pair repulsion. We'll define that on a slide. And the geometry of molecules. So when we're drawing Lewis structures, we're representing a molecule in a 2D drawing, but molecules, most molecules, are not 2D shaped. So for example, if we draw CH4, which is methane, carbon has 4 bonds, 1 to each hydrogen atom. The way we draw this Lewis structure indicates that the molecule is flat with the plane of the paper, and bond angles are 90 degrees. That is not how methane exists in nature. Remember that electrons are all negatively charged. There are electrons in each of the bonds to hydrogen, from carbon to hydrogen. Negatively charged electrons in a bond repel other negatively charged electrons in other bonds. So in 3D space, the bonds between carbon and hydrogen will separate, they'll get as far apart away from each other as possible because of the electron pair in one bond repelling electron pair in another bond. So in our 3D world, methane exists in a tetrahedral shape where we have carbon in the center, and then hydrogen is, each of these bonds are as far apart as possible, and that results in a tetrahedron where we have 4 quarters of this shape here. In a tetrahedron, the bond angles are now 109.5 degrees, and that's the largest bond angle that can exist, so that all bond angles are equal. If you were to make one bond 110 degrees, then you're making the other 2 bonds closer to each other. So space filling model, remember this shows the orbitals overlapping, the valence shell orbitals overlapping. All-in-Sig model emphasizes the bonds, and then here we have this tetrahedron overlapping that all-in-Sig model. You can also draw 3D shapes, right? Can't really draw that. At least I can't draw that. But we can represent 3D shapes with wedges and dashes. The wedge represents, if you're looking at the paper, this bond is coming out towards you, just like this atom is coming out towards you. And then the dash represents an atom going away, just like this one. We won't do this in our class. You'll definitely see this again in chemistry, though. Okay, so this is a result of those electron pairs in bonds repelling each other. This is VSEPR, valence shell electron pair repulsion. So the spatial arrangement of bonds must minimize this repulsion. So minimal electron-electron repulsion is accomplished by keeping chemical bonds as far apart as possible. So for methane, for something with 4 bonds, that is a tetrahedral shape. We can use the number of bonds and lone pairs present in an atom or on an atom to determine its geometry. We call these electron pair domains. So electron pair domain is a set of electrons that occupies a particular region around an atom. So a domain can be a single bond, a double bond, a triple bond, or a lone pair. Each of those individually are one electron pair domain. That's one region that those electrons are occupying space. A ligand is defined as an atom or group of atoms that are bonded to an inner atom. So if we think about methane, which we've looked at, the inner carbon has 4 single bonds. Each of those count as one electron pair domain. So carbon in methane has 4 electron pair domains. Each of those electron pair domains represent a bond to a ligand, so it has 4 ligands as well. Something like water, draw this more towards the bottom here for space. In the H2O, the central atom oxygen has 2 bonds and 2 lone pairs. So it also has 4 electron pair domains. But only 2 of those domains are bonds to ligands. So it only has 2 ligands. So it has 2 ligands, 2 lone pairs, and that makes up the 4 electron pair domains. So we'll use number of electron pair domains, number of lone pairs, number of ligands to determine the shape of a molecule. The steric number, you might see this word, steric number of an inner atom is the number of electron pair domains. So steric number of carbon in methane is 4. Steric number of oxygen in water is also 4. We have 3 basic overarching electron arrangements that we'll talk about. There are more, but we're just going to talk about these 3, which cover most of the molecules you see in art class and organic chemistry. First is if we have 2 electron pair domains. So this is something like carbon dioxide in that carbon central atom. That carbon has 2 double bonds. 1 double bond is 1 electron pair domain. So carbon has 2 electron pair domains. For those 2 electron pair domains to be as far apart as possible, they can be 180 degrees apart. So the bond angle with 2 electron pair domains is 180 degrees, and we call this geometry linear. Now when we count electron pair domains in a molecule, that atom that has, in this case, 2 electron pair domains, hybridizes or combines valence shells to be equal. So if there are 2 electron pair domains, 2 valence shells are combined. We're talking about mostly atoms in the second period. Their valence shells are the s orbital and the p shell, which includes 3 orbitals. The s shell is always hybridized. If you have 2 electron pairs, then you hybridize the s shell in one of the p orbitals. So the hybridization is sp, 1 s and 1 p. 1 s orbital and 1 p orbital. So this is the combination, we'll say. Or the hybridization of valence shells involved in bonding. Next, if we have 3 electron pair domains, an example of this would be formaldehyde, which we drew the Lewis structure last class, I think. Yeah, I think it was this Wednesday. This carbon in the center of formaldehyde has 3 electron pair domains, single bond, double bond. For these bonds to be as far apart as possible, they can achieve a 120 degree bond angle. That molecule is planar, so all bonds are on one axis, and they form a triangle. So the shape of this is trigonal planar. Now the central atom here has 3 electron pair domains, so it hybridizes an s orbital and 2 p orbitals. Its hybridization is sp2. Molecule with 4 electron pair domains like methane We already talked about the shape. This can become a tetrahedron. Takes on a tetrahedron shape. Bond angles are 109.5. And then that central atom has 4 electron pair domains. So the s and all 3 p orbitals are hybridized to form equivalent 4 equivalent orbitals. And so that will be, we call sp3. Okay, so we'll talk about each of these rows a little bit more detail. First, tetrahedral 4 electron pair domains, and then we'll get to 3 and 2 electron pair domains. Let's start with this bullet point here. All molecules with 4 electron pair domains have tetrahedral electronic geometries and are sp3 hybridized. So if you have 4 electron pair domains, you've got sp3 hybridization. The electronic geometry includes bonds and lone pairs. So here's water. We have 2 lone pairs on oxygen and 2 bonds to hydrogen. There are 4 electron pair domains. That molecule takes on a tetrahedral electronic geometry. Its molecular geometry is different, and we'll talk about that in a second. So these are, oops. Okay, so each of these listed are the molecular geometries, but all of them have tetrahedral electronic. First, if we have 4 bonds, so we have 4 electron pairs, electron domains, and all of them are ligands, none of them are lone pairs. Then the geometry of the central atom and the other atoms bonded to it is tetrahedral. That's the molecular geometry and the electronic geometry. Bond angles are 109.5. We have a different molecule that still has 4 electron pair domains. It still has tetrahedral electronic geometry, but one of those electron pair domains is a lone pair. Then the molecular geometry does not consider the lone pair because there's not an atom at the end of it. So molecular geometry, we're talking about atoms bonded to that central atom. So here we have 3 atoms bonded to the central atom. We have a trigonal pyramid shape because the 3 atoms down there are lower than where the central atom is. Now the bond angles here are less than 109.5. We won't put an actual value to it, but what's important to remember, the key concept is that these bond angles between the atoms bonded to the central atom are less than 109.5, so lower than tetrahedral bond angles. And that's because we have a lone pair. The lone pair takes up more space than a bond would. So the lone pair repels the other bonds. You might think of like, here's the trigonal pyramid. Lone pair at the top pushes the bonds a little bit closer to each other. So there's a smaller bond angle between the atoms bonded to the central atoms. And then if we have another atom, 4 electron pair domains, 2 of them are lone pairs, 2 of them are bonds. Then we have a bent molecular shape. We just have 3 atoms that are bent in its molecular shape. And again, the bond angles are less than 109.5 because of the lone pairs. So an example of a bent molecular geometry is water. 4 electron pair domains, 2 are lone pairs, 2 are bonds. Electronic geometry is tetrahedral. Molecular geometry is bent. Ooh, we gotta move fast. Okay, let's go to the next slide. So electron group geometry or electron pair geometry describes the 3D arrangement of valence shell electron groups. This includes lone pairs and includes all the bonds. The molecular shape describes the 3D arrangement of outer atoms on the central atom. So water, tetrahedral electron geometry, but bent molecular shape. When you are determining the molecular geometry, you need to first draw the Lewis structure to see how atoms are bonded. You can use the Lewis structure to determine the number of electron pair domains. This will also tell you hybridization. This will tell you electronic geometry. So electronic geometry and hybridization you can determine by just determining the number of electron pair domains. To determine the molecular geometry, you use the ligand count, so the amount of other atoms bonded to that central atom. I think we have just enough time. We'll be good here. So if we have 3 electron pair domains, we said this is trigonal planar electronic geometry. If all electron pair domains are bonds, are ligands, then it also has trigonal planar molecular geometry. Bond angles are 120 degrees. If one of those electron pair domains is a lone pair, we can draw this lone pair occupying some orbital. Then again, we have a bent geometry. All molecules with 3 electron pair domains have trigonal planar electronic geometries and are sp hybridized. And lastly, we have linear. If you have an atom with 2 electron pair domains, it has linear electronic geometry, it has linear molecular geometry, and they are sp hybridized. So we looked at carbon dioxide, which is shown over here. Linear molecular shape, 180-degree bond angle. On the left, we have another example. Here we have a zinc atom in the center bonded to 2 carbon atoms. Zinc has 2 single bonds, so it has a steric number of 2. It has 2 electron pair domains. It has linear geometry. But how about the carbon? The carbon that's bonded to the zinc. What's the geometry of that carbon? So this one up here. What's the geometry of the carbon bonded to zinc there? We have an atom with 4 bonds. That carbon has 4 bonds. Has 4 electron pair domains. All of them are bonds, so it has tetrahedral geometry. So if you have multiple atoms bonded to multiple other atoms, like in this case we have zinc bonded to 2 carbons, carbon bonded to 3 hydrogens, each of those atoms that has multiple bonds has its own geometry. So we describe geometry for an atom. But something like carbon dioxide, we can only describe the geometry of carbon. So we say the molecule has linear geometry. All right, next slide, we have a summary of these molecular geometries. The first column is steric number, and we've only talked up to steric number 4, so you won't be asked about 5 and 6, but there are larger atoms that exist, or larger molecules that exist. So you should know how to determine electronic geometry, molecular shape, and remember like the bond angles for tetrahedral, trigonal planar, and linear. We can add hybridization here. So if we have 2 electron pair domains, hybridization is sp. We have 3 electron pair domains, hybridization is sp2. 4 electron pair domains, hybridization is sp3. Okay, last couple of minutes. Let's do the very last slide. So the shape of hydroxylamine, the Lewis structure is already drawn for you. We can't really describe the shape of hydrogen because hydrogen has one bond and that's it. No other lone pairs or anything. So in this molecule, identify the number of electron pair domains for nitrogen and oxygen, the electronic geometry of nitrogen and oxygen, and the molecular geometry of nitrogen and oxygen. Okay, nitrogen. How many electron pair domains around nitrogen in this molecule? 4. We have lone pair, 3 bonds. Each of those are 1 electron pair domain, so we have 4 total. So with that, what's our electronic geometry? Tetrahedral. Three of the electron pair domains are bonds. So we have 3 ligands. We have 1 lone pair. So what's the molecular geometry with 4 electron pair domains and 1 lone pair? Trigonal pyramidal. Now how about oxygen? How many electron pair domains on oxygen in this molecule? 4, 2 lone pairs, 2 single bonds. So it's electronic geometry. Same thing, tetrahedral. It has 2 ligands. Oh. So molecular geometry, if we have 4 electron pair domains, 2 of them are lone pairs, 2 of them are ligands, that is bent. All right, thanks everybody. We are done. So we can review the other pages that we didn't get to today. So the previous example and the bond energy example on Monday, that will be online. Those are good questions to bring if you'd like to review them. Don't forget your assignments that are due. And please fill out course evals. So it only takes a few minutes. It's anonymous. Your instructors won't know who left what comments, but it's really valuable to us as instructors. We want to know how the class is for you, so please take a few minutes to fill that out for us. I think it's due Monday, maybe Tuesday. It's been a good semester. Yeah, thank you. Thanks. Yeah. Yes. Let me.
Will the final be in